This lecture covers the fourth cyclomatic process, evaporative cooling, and then capacity of humidifiers and capacity of cooling and heating coils. Fourth cyclomatic process, adding moisture without the addition of heat. So this is also called as evaporative cooling process. So on the left hand side we can see figure at state number 1 and at state number 2. At state number 1, the dry bulb temperature 1, humidity ratio 1, enthalpy 1, and relative humidity 1. And at state number 2, dry bulb temperature 2 condition, humidity ratio 2 condition, H2, and relative humidity 2 condition denoted by 5. But H1 will be equal to H2 in this case because this is evaporative cooling process, and this is also called as a constant enthalpy process. So in this process the line will follow the constant enthalpy line. So the H2 will be equal to H1, and in the middle the water is shown. So it is the humidification or dehumidification. So the practical example is we can say of a desert cooler. Here we are only adding water, and by the addition of water cooling is being experienced. So this process is called as evaporative cooling process. Evaporative is achieved by passing outdoor hot air through a water wetted medium to permit an adiabatic process. As the dry hot air passes through the wetted medium, it evaporates its water and gets cooled itself. Evaporative cooling process follows the wet bulb line on a cyclometric chart. The enthalpy of air stream remains constant in this case. Total reduction in temperature through evaporative cooling is called wet bulb depression, WBD. So the wet bulb depression is equal to dry bulb temperature minus wet bulb temperature. Wet bulb depression is equal to the maximum temperature difference that an engineer can obtain with an evaporative cooling system. However, the efficiency is equal to 80% of wet bulb temperature under practical condition. The efficiency of evaporative cooler is equal to the ratio of the difference between dry bulb temperature 1 and dry bulb temperature 2 with wet bulb depression. So mathematically, efficiency is equal to dry bulb temperature 1 minus dry bulb temperature 2 divided by dry bulb temperature 1 minus wet bulb temperature, or dry bulb temperature 1 minus dry bulb temperature 2 divided by wet bulb depression. Therefore, the equation will become dry bulb temperature 2 will be equal to dry bulb temperature 1 minus efficiency into wet bulb depression, that is dry bulb temperature 1 minus efficiency into dry bulb temperature 1 minus wet bulb temperature. So a practical example 4, to explain the evaporative cooling example. Let the dry hot air has dry bulb temperature 1 as 35 degrees Celsius and 20% relative humidity. So from cyclometric chart, the wet bulb temperature is found to be 18.8 degrees Celsius. Then wet bulb temperature is equal to dry bulb temperature minus wet bulb temperature. It is equal to 35 degrees Celsius minus 18.8 degrees Celsius is equal to 16.2. So an 80% efficient evaporative cooler will cool the air by 16.2 into 0.8 is equal to 12.96 degrees Celsius. Therefore, the exit air from cooler will have dry bulb temperature as dry bulb temperature 2 is equal to dry bulb temperature 1 minus wet bulb depression into efficiency. So it is equal to 35 degrees Celsius minus 12.96 96 degrees Celsius is equal to 22.04 degrees Celsius. Example 5. The outside atmospheric air conditions are dry bulb temperature 1 is equal to 28.1 degrees Celsius and relative humidity 1 60.1%. Design an air conditioning plant to supply air to the farm storage to fulfill the following conditions. Air volume flow rate will be equal to 70 cubic meter per minute. Inside storage air dry bulb temperature is equal to 20.9 degrees Celsius and storage air relative humidity should be 55.1%. So when the term design is coming, it means that we are supposed to calculate the load of cooling coil, load of heating coil, and the capacity of humidification or dehumidification. So here the two set of data, state point number 1, the atmospheric air and the storage condition have been given, and we are supposed to calculate the capacity of heater, capacity of cooling coil, and the capacity of humidifier. So locate on psychrometric chart point number 1 against relative humidity of 60.1% and dry bulb temperature as 28.1 degrees Celsius. And also point number 2, relative humidity 55.1% and dry bulb temperature as 20.9 degrees Celsius. So find on the psychrometric chart, we plotted these 2 points, and state point 1 and 2 have been drawn, and a line is connecting, is the process line has been drawn also. So the values of W1 was found to be 0.0143 kg of water divided by kg of dry air, and W2 is equal to 0.009 kg of water divided by kg of dry air, and enthalpy 1 64 kg per kg of dry air, and enthalpy 2 45 kilojoules per kg of dry air. For required air supply rate of V1 is equal to 70 cubic meter per minute into the storage, the specific volume of air at point number 1 has to be determined, which is found to be 0.875 cubic meter per kg of dry air. So this specific volume is determined in order to convert the volumetric flow rate into the mass flow rate, which is required for this numerical problem. So after determination of specific volume, air mass flow rate is equal to m prime is equal to v prime over v1. So 70 divided by 0.875. So it means that a volumetric flow rate of air divided by specific volume of air is equal to 80 kg dry air per minute. So water drained out mean capacity of humidifier, dehumidification or dehumidification process. MW prime is equal to MA prime into W1 minus W2. It means we will put the value of 80 in MA and then put the value of W1 and W2, and the answer is moisture removal rate or capacity of dehumidification was found to be 0.424 kg of water per minute. So heat removal rate Q prime is equal to MA prime into H1 minus H2. It comes to be 1520 because the value of mass flow rate is 80 of air, and enthalpy at point number 1 64 and point number 2. So by putting the value here, the answer comes to be 1520 kilojoules per minute. So this is how to design a system for a cyclometric process. When the data is given, example 6, design an air conditioning plant for a food industry with the following conditions. So air condition room outside existing, and room inside required. So dry bulb temperatures are given at point 1, 30.2 degrees Celsius, at point number 2, 20.1 degrees Celsius, and relative humidity at point number 1, 74.5%, and at point number 2, 60.5%. The AC plant absorbs air with volumetric rate of 20.1 cubic meter per minute. So design mean again the capacity of cooling coil or heating coil and the capacity of humidification or dehumidification. So we will solve now. So first of all, we will draw the sensible cooling process as 1 into 1 star. Then dehumidification process 1 star to 2 star, and then sensible heating process 2 star to 2 process. Basically, the process line will be drawn between 2.1 and 2, and the other point are the steps actually we will have to follow based on the type of cooling being taking place. So on cyclometric chart, locate point 1 and 2 and find air cyclometric properties. So these had been presented in the form of a table. So dry bulb temperature at point number 1, our value was 30.2, relative humidity was 74.5. So the absolute humidity was calculated, humidity ratio 0.02. Enthalpy is also calculated, 82 kilojoules per kg of dry air, and we will also have to calculate the specific volume point, because this value will be used to convert volumetric analysis into mass flow rate. So its value was found to be 0.89 cubic meter per kg of dry air. So at point A star, 1 star, sorry, the absolute humidity will remain the same as has been presented in the second row of the table. The relative humidity will reach the 100% at saturation point. So this will be the dew point. Up to dew point, the absolute humidity or humidity ratio will remain constant. So at point number 2 star, again the line will follow the dew point line at 100% relative humidity. However, the absolute humidity value will be changed. Its value was 0.009 kg of water per kg of dry air. And at point number 2, the dry bulb temperature is 20.1 and relative humidity is 60.5, and absolute humidity will remain the same, and enthalpy was found to be 43 kilojoules per kg of dry air. So on the cyclometric chart, we see that locate point 1 with relative humidity 74.5% and dry bulb temperature 30.2, and found humidity ratio 1.021 kg of water divided by kg of dry air, enthalpy 182 kilojoules per kg of dry air, and specific volume 0.85 cubic meter per kg of dry air. So also located point 2 with relative humidity 60.5% and dry bulb temperature as 20.1%, and found W2.009 kg of water per kg of dry air and enthalpy 34 kilojoules per kg of dry air, and air mass flow rate is calculated by using the formula MA prime is equal to VA prime over V1, which is the specific volume from cyclometric chart. So 20.1 divided by 0.89, the answer comes to be 22.58 kg of dry air per minute. So this is the mass flow rate of the air which is required for the formula. So the capacity of a cooling coil is calculated by process 1 to 2 star and to 2 star, and Q1 prime is equal to MA into H1 minus H2. So 22.58 is the mass flow rate, and change in enthalpy from 80 H1 is 82 and H2 is equal to 34. By putting the value, the answer comes to be 1084 kilojoules per minute. And we will divide this answer because the unit is kilojoules per minute, and in order to convert into tons of refrigeration, TR, we will have to divide by 210 kilojoules per minute. So answer comes to be 5.16 tons of refrigeration. So the heating rate process 2 star to 2, Q2 star is equal to MA into H2 star minus H2 is equal to 22.58 into 43 minus 34 is equal to 203.256 kilojoules per minute. It is equal to 203.256 kilojoules per second. So kilojoule per second is called as kilowatt. So our answer comes to be 3.39 kilowatt. Then water removal rate or the capacity of dehumidification. This formula is MW prime is equal to MA prime into change in humidity ratio, that is W1 minus W2. So by putting the value here, 22.58 into 0.02 minus 0.009, the answer comes to be 0.25 kg of water divided by per minute. 0.25 kg of water per minute. This is the moisture removal rate. So now we have designed all the required parameters with the help of psychrometric chart. Another example, the atmospheric air at 1 bar pressure has dry bulb temperature 28 degrees Celsius and relative humidity 32.23%. Determine the other 5 thermal properties of the air. So the given TDB 28 and relative humidity 5 32.23%. Locate air state point. Locate air state point 1 on the psychrometric chart by going vertically upward from dry bulb temperature 28 degrees Celsius and stop it as it intersects the relative humidity curve of 32.23%. Absolute humidity, move horizontally to right hand side and read on the y-axis as W is equal to 0.0057 kg of water divided by kg of dry air. For dew point temperature, move horizontally to left hand side and stop at saturation curve to read dry bulb temperature, dew point temperature, 9.93 degrees Celsius. Wet bulb temperature, move along constant wet bulb line, oblique up left hand side and stop at saturation curve to read T wet bulb temperature as 17 degrees Celsius. Enthalpy, move along constant enthalpy line, oblique up left hand side and stop at enthalpy scale to read H is equal to 47.48 kilojoules per kg of dry air. Specific volume, interpolate between the specific volume lines and read V is equal to 0.863 cubic meter per kg of dry air. So this is how we plot different points. We plot a state point on psychrometric chart and determine the other undefined parameter or other parameters which we want to calculate from psychrometric chart. This is the manual way of calculation by locating a point with a pencil and then locate the other point and find the other points. But as explained earlier that different softwares are available nowadays. One example is SciPro. Just draw a state point electronically and then on the left hand side bar all parameter will come and they will tell all the other parameter like enthalpy, specific volume, wet bulb temperature, dry bulb temperature, dew point temperature, etc. And one can draw very precisely on this one. And there is also option to in FPS system, in SI system, at sea level, at little bit hilly areas. So we can select our location from that point. So it's best option, instead of going to manual system, we should solve the numerical on Pro or other software available in the market. So capacity of humidifier. Capacity of humidifier or moisture removal rate is calculated by following equation. Capacity of humidifier is equal to mass flow rate times change in the humidity ratio, where m prime is the m a prime is the mass flow rate of dry air, and w1 is the humidity ratio at point number 1, and normally this is the higher values. And w2 humidity ratio of point 2, normally it's lower value, and ma is the mass flow rate. Capacity of heating and cooling coils. Capacity of heating or cooling coil in kilowatt is given as under Q prime or C is equal to M prime A into H1 minus H2, where C is the capacity of heating or cooling coil in kilowatt. H1 enthalpy of zero point 0.1, normally it's higher value point. Its unit is kilojoules per kg, and H2 is the enthalpy of point number 2, normally the lower point, and its unit is kilojoules per kg, and M prime A is the mass flow rate of air in kg per second.